This is the best attended seminar this year, and no wonder, because we have Geoffry Hinton here as a speaker. He received his PhD in experimental psychology from Cambridge, and BA, I'm sorry, and a PhD in artificial intelligence from Edinburgh. And he did postgraduate work at Sussex at the University of Southern California. And I know him as a professor at the computer science department of Carnegie Mellon, where he was the advisor of Peter Brown. Anyone of you know Peter Brown, anyway, who used to be a big contributor to speech recognition and now to Wall Street. And Geoff is now at the Department of Computer Science at the University of Toronto. And he's going to talk to us about learning energy-based models of high-dimensional data.
I should correct one thing you said. Peter contributed to language modeling, but he intends to take away from Wall Street.
That's what accounts for the drama market.
Okay, this is my first ever talk using PowerPoint. I decided I'd better get into this century. And so, excuse me if things go wrong. The work I'm going to talk about today was joint work with a postdoc called Max Welling and two graduate students called Guy White and Simon Osindero. So there's various reasons why one might try and do unsupervised learning on data. One reason is you'd like to respond to the data in a sensible way, like if you're an organism, and it might be sensible to respond to the causes of the data rather than to the raw sensor readings. If you're a statistician, it might be nice to try and understand what the data is about, and hidden causes are good for that. And if you're a neuroscientist, it would be really interesting if neurons in the brain really did represent causes of data. I'm a bit dubious about that. But there's a different kind of hidden structure. Instead of looking for things that cause the data, where we have some causal generative model, and we say the data is the result of running this stochastic model, and we think about it in those terms, we might try and find a different kind of factor. We might say that data, particularly data like images, but also maybe language, is characterized by having lots of constraints. And these constraints are typically satisfied. Like if you look at the intensities in a patch of an image, typically, if you apply a little filter that sort of subtracts the surround from the middle, you'll get almost exactly zero. That will happen wherever there's a smooth piece of image. And it'll go wrong where there's an edge, but that's a rare event. And so you might say images are characterized by having these constraints that are frequently approximately satisfied. And when they go wrong, they may go very wrong, so we don't want a kind of Gaussian model of the distribution of those constraint violations. But this is a different kind of way to characterize images. Now in language you have the same. You might try and characterize sentences by saying there's some features that contribute, and we might think of them as energies, log probabilities, and we'll characterize what makes a good sentence by saying good sentences are ones that have these good features and don't have these bad features. So what are called maximum models are in this class. And what I'm going to talk about today is I'm going to start off by talking a little bit about causal models and say what their problems are, and describe a little bit of work I did with Radford Neal, just very briefly, on how to overcome some of those problems. And then I'm going to make a big analogy and say energy-based models like this also have problems, these kind of constraint-based models, and maybe there's a similar trick for overcoming their problems. So here's some types of density model. There's these stochastic generative models. There might be context-free grammars, there might be HMMs. In these models, it's very easy to synthesize an example from the model, to get an unbiased sample of what the model believes in. If the model is more complicated than something that has some discrete distribution over hidden variables, or some Gaussian distribution over hidden variables, then analysis can be very hard. This is in the old English sense of analysis by synthesis. Analysis can be very hard because the posterior distribution over all these hidden causes that you believe created the data can be a messy thing. And it typically will be if you use nonlinear and distributed representations there. That is, you think there's many things at once causing the data, and they have a nonlinear relationship to the data. That's certainly true for things like images, where there's several objects at once, and the relation between properties of an object like its orientation and the pixel intensities is very nonlinear. If you can get samples from the posterior distribution, or some representation of the whole posterior distribution, then learning is easy. You can learn all these conditional probabilities by which one thing affects another. So that's the problem for these kinds of models. Long before I knew about these, Terry Sinofsky and I got interested in a different kind of model. We didn't actually have any statistics at all about that. Well, Terry knew a little bit and I knew none. So we sort of made up this stuff. It turned out to be called Markov random fields. And we had these things called Boltzmann machines, in which synthesis was hard, analysis was hard, and learning was hard. And we both got tenure on those. They're amazing. I'll argue a bit later that you can simplify these a bit in a direction Paul Smolensky suggested years ago, that make them tractable, but I'm not going to really talk about that today. I'm going to talk about these kinds of models. So in these models, you characterize data by saying each data vector is going to get some energy. The model's going to assign some energy to it, and the probability of the data vector is going to be proportional to e to the minus the energy. Except here it's a free energy, and you have stochastic hidden variables. It's much simpler if you have deterministic hidden variables, and that's like the max-end models, where the features are typically a deterministic function of the data. And you want to characterize the data in terms of e to the minus the energy that the features give it. It's hard in these models to do synthesis, and it's going to stay hard. I can't see any way around that. That is, getting an unbiased sample from a model of this kind is tricky. Physicists have recently come up with very clever tricks called coupling from the past to come up with
Say it again.
coupling from the past. Physicists called Wilson and Propp have come up with very clever ways of getting unbiased samples in only moderately huge amounts of time from these kinds of models. And genuine unbiased samples, but I don't think that's relevant for learning because it's too slow. Analysis in these models, when it's a deterministic model, is very easy. You just put in the data and activate the features, and that's your analysis. Your characterization of the data is to say it has these features, and that's it. And also you can compute its energy. So up to an unknown offset, you can say what its log probability is. The big question of this talk is learning easy or hard? And on the face of it, it appears to be hard. It might be easier if instead of learning the features themselves, we just learn some weights on the features, which is what the max-ed people do. Even that's quite difficult. And I'm going to argue that actually, maybe learning is relatively easy in these models, using an approximation. So, just to quickly go over the causal models, the typical Bayes net, you have these hidden causes, you have conditional probability tables on these arcs of some kind, and these you pick at random, these provide conditional probabilities, these you pick these, and then those provide inputs to those, and you pick those, and hey presto, you've got a data, you've got a sample from your model, and it's hard to get the posterior over these guys if I give you those guys in the parameters. It's all non-linear. So what idea you might have for learning that kind of causal model, Bayes net, is to say, well, getting the true posterior distribution is a mess. What if we assume that the posterior distribution is actually simpler than we know it really is? What if we assume it factorizes, for example, into a product of separate posterior distributions, one over each hidden variable? And we use that approximation when we do learning. So when we're doing the sort of M step of EM, when we're changing the parameters to maximize the probability of the data given the model, we assume that this incorrect posterior is actually the right one, and we do the maximization. Well, on the face of it, that's a dangerous thing to do, because if you're using the wrong posterior, when you so-called improve your parameters, things might actually get worse. You might decrease the probability of the model generating the data. But now maybe there's some other function that you're improving, and some other sensible function, and you can guarantee, in the expected sense if you're sampling here, guarantee that this other function will tend to improve. And as many of you know, there is another function. So this is the term we normally maximize when we're fitting a model to data, the log probability of the observed data given the parameters of the model. That's how well the model fits the data. And we're going to have a new objective function, which isn't just this, it's this penalized by something else. And we're going to penalize it by the KL divergence between the true distribution over the hidden variables in the model, given the data, and I guess I should have put a theta in there, given the parameters of the model. So this is the posterior distribution over the hidden variables given data t. And this is our approximation to the posterior distribution. Now if we use the true posterior, this term would be 0, and we'd be back to maximum likelihood fit. But actually, if we're using a wrong posterior, then this term will be non-zero, and this will be a lower bound on the log likelihood. It will always be less than log probability. It will act as a lower bound. And now if we use product distributions as an approximation, although we can't compute the derivative of this with respect to the parameters, and we can't compute the derivative of this with respect to the parameters, we can compute the derivative of the difference. So you've got two intractable things whose difference is tractable. And so we can change the parameters so as to increase this thing. And what will happen is, when this thing increases, two things might happen. The log probability might increase. That's good, that's what we really want. Or it might go down, but the log probability can only get worse if this thing gets a lot better. And this is a measure of how badly inference is working in our model. So at least when the log prob of the data goes down under our model, we've moved to a point in model space where inference works much better, where our approximating distribution is a much better approximation to the true posterior. And so that seems like a good trade-off. And this actually, if you think about it, both of these can be measured in bits. This is quite a good measure. It's basically how good is our model and how easy is our model to do inferencing. And if we had a model that was completely impossible to do inferencing but was pretty good, that's no good to us. If you have a model that's no good but easy to do inference, that's no good. What we want is the best trade-off between these. So that's a pretty sensible function to use. And the surprising thing is you really can do gradient ascent in this combined measure, which is sort of peculiar because it seems odd initially to put the tractability of inference in a model into the same equation with how well the model fits the data. They seem a bit like apples and oranges, even though they're both in bits. Okay. So my take on all that is that was a very nice story. How well it works in practice remains to be seen. Lots of people doing graphical models are now using this kind of approach. It's called the variational approach. And it works quite well in some cases, not so well in other cases. The real question is, if I have a complicated non-linear distributed representation of data, and I then use these simple approximating distributions, do I basically throw away a lot of the value I get from this complicated model, or can I still get a lot of the value from the complicated model and still have these simple approximations? And I think that's just an empirical question. And luckily there's lots of other people investigating it. And the math, they're getting bigger and bigger equations, so it's time to move on to something else. Okay, so here's an energy-based model. And it's a deterministic one. So in a Boltzmann machine, these would be stochastic hidden units, like latent variables. Here, these are not latent variables. Well, I don't like to think of them as latent variables. Maybe you're thinking like that. I don't know what the correct terminology is. Given the data, then there's some deterministic function that determines how, I think of these as neurons for now, how active each of these guys gets. And it's got some non-linear relationship between the activity and the data, typically, some smooth non-linearity. And then each activity here contributes some energy, and maybe you could have a lambda on that little blue arrow that you learn. And the energy of the whole data vector is just the sum of all these energies. So it's log linear in that sense. It's just that this network will be quite a complicated network with multiple layers of non-linearities in it. So the parameters are certainly related to the probability of the data in a complicated way. And it's obviously very easy to compute the energy of some data. You just go forwards through the network computing the activities, and then add up these energies, and that's it. And we'll just define the probability of the data. If it was discrete data, we could use a sum. I should really use an integral because I'm going to be using continuous data. But we define the probability of a data vector as e to the minus 6 energy, normalized by the sum over all possible data vectors. And this thing is our partition function, and this is what makes life nasty, because we're going to have to estimate derivatives of that. So, maximum likelihood learning would require maximizing the sum over all data vectors. I've left out the sum over data vectors here, of this thing. So that means we want the energy of the data vector to be small, and we want the energy of its rivals to be big. And if you take derivatives of the log prob, this one's obviously easy. This term here, with a little bit of manipulation, turns into this. Notice this is of exactly the same form as that. So this is saying, lower the energy of the observed data, raise the energy of all the competition to the observed data, but focus on the strong competition. So under your model, under your current model, this is the probability of generating each of the competitors. The competitors that your model doesn't currently fancy, you don't need to bother about those. You need to worry about the ones that it thinks are really good, and you need to push those down by raising their energy. push their probabilities down. Now this thing is hard to compute, because this thing, if you look at the previous transparency, P of C has all this normalization term. So that just by itself is a mess. So not only do we have a sum here over exponentially many alternatives, or over the whole data space, but each thing inside this sum's a mess itself. And there's an obvious thing to do now. Anybody who knows about Markov chains would say, well, the obvious thing to do here is to get samples of this from a Markov chain. And if you run the Markov chain to equilibrium, to the stationary distribution, then the unbiased samples. So although you're going to get some noise in estimating this, because there's going to be noise here, a lot of noise, at least you can get an unbiased sample of this gradient, and maybe if you crawl down it very slowly, you'll be able to improve your model. But obviously, if it wasn't for the fact that you have to sample this using a Markov chain, and if it wasn't for the fact this was a very large sum, life would be easy, but as it is, life's a mess. And so the point of this talk is, what can we do about that? And I'm actually not going to give you a very satisfying answer. That is, I'd love to have some mathematics that says, we do these manipulations, it all goes away and it comes out blah, blah, blah. I'm going to give you something that works, and I'm going to give you some intuitive motivation that it works, but you're going to probably be able to tell by the end of this talk that I originally trained as a psychologist. Okay. If we're working in a space where you have continuous real-valued inputs, and then deterministic hidden units, you can't do things like Gibbs sampling. In Gibbs sampling, you fix the visible variables, and then you update the hidden variables. They have to be stochastic for that. We can't do that. But we can use a technique called hybrid Monte Carlo. So what we would do, the obvious Markov chain, the really simple one, would say, take the data, perturb the data, add a bit of noise to it somehow, compute the energy of that perturbed data. If the energy is higher, then occasionally accept. If the energy is lower, always accept. If you do that right, then that'll be a Markov chain that eventually converges to the equilibrium distribution of the data. But in a high-dimensional space, that's very inefficient. In particular, if you have, say, an image which satisfies lots of constraints, and if these hidden units represent violations of these constraints, if you move in a random direction, if you take any pixel, if you take all the pixels in an image and move them in a random direction, you'll almost always make it a lot worse. And so it'll be very hard to find moves that you're going to accept. And so in high-dimensional spaces, the obvious Markov chain is very inefficient. It'll diffuse very slowly over flat regions, it can't cross barriers, and in a ravine, it'll almost certainly produce a candidate that's no good and you'll never accept. The physicists came up some time ago with a much better method that makes use of the gradient. All applied mathematicians know that wandering around at random in a high-dimensional space is nearly as good as wandering around using a gradient, particularly things like ravines. And the physicists came up with a way of using this when you're doing Monte Carlo, and this makes it scale much better. Roughly speaking, it's got almost linear scaling. That is, if you double the size of the input, you don't have to do lots more rejects this way. You can make steps that are almost as big and accept almost as often. And you can cross energy barriers because you can have momentum here. So hybrid Monte Carlo is going to work much better. And to explain what hybrid Monte Carlo is, it's probably best just to show you a picture. So this is actually a little network we learned, and this is towards the end of learning. It's just got two-dimensional input data. And so these are the two components of the data vector. It associates with each data vector an energy, which is the height here. And the aim of learning is to construct this energy surface over the space so as to achieve low energy. It's actually trying to achieve a ridge of low energy here, a ridge of low energy here, and a ridge of low energy here. And it's more or less achieved it here. And hybrid Monte Carlo says, start with a data vector like this one, add a little bit of random momentum, just drawn from the right distribution. And so these are three different random momentums you might have added. And once you've added the random momentum, then follow the trajectory that a particle on this surface would have, and follow it for a whole bunch of steps. And by following it for a bunch of deterministic steps, you can kind of beat diffusion. You can go quite a long distance. You're not just randomly diffusing around. You get an n versus root n win there. And so, for example, this thin trajectory here, you can see it goes downhill, and then it goes up over this ridge and down here, and then up here, and it starts turning away from this ridge here. You can sort of see it following the dynamics. And so it will tend to, it'll be able to go over ridges, but it'll tend to stay in very low places. Having done that for a while, what you ought to do then is stop, take the momentum that the system's got, throw it away, and give it a new momentum. And that's how you get rid of energy. Because obviously if I started up here, I go shunk. By the time I got here, I'd have enormous momentum. And when I stopped and gave it new momentum, that would throw away lots of energy. So that's how you get rid of energy here. And basically if you keep doing that, that's a Markov chain that will in the end sample from the equilibrium distribution. So at each step you take some random momentum, follow the dynamics for a while, then throw your momentum away and get more momentum. And you have to do a little computation to see whether you got numerical errors when you follow the dynamics. And if you did, you reject that. If you take small enough steps, you won't get numerical errors, so you can always accept.
So and this momentum is a function of the smoothness of your energy landscape?
No, it's just momentum drawn from some Gaussian distribution. And when you start, you have the same distribution of momentum as when you finish. One thing that does change is the size of the steps you can use when you follow the dynamics. Because the idea is you've got a gradient and you're trying to follow dynamics on a curved surface. You use a leapfrog method, which is basically good to second order rather than first order, so that you can deal with the curvature moderately well. But complicated twists and things you can't deal with. So you have to do small steps, and as the surface gets more and more convoluted, you have to make those steps smaller and smaller. To begin with, you can make them big. And you typically, what we do is we adapt the step size so you'll accept 90% of the time. Because you want to go as far as you can without getting numerical problems.
If the distribution from which you sample momentum has variance 0, then this reduces to gradient descent, right? Which is not a Markov chain.
Actually, no it doesn't. No?
Then I've misunderstood something.
Okay, because in gradient descent you'd never go uphill again. And even if I started here with momentum 0, I could go down, I then have momentum, and then I come up over a ridge.
Oh, okay. Yes, I'm sorry. So the momentum vector gets updated as you go.
Yes.
Yes. Right.
You're simulating what would happen with a real particle.
Okay. Nonetheless, so it produces gradient descent with momentum, but that doesn't converge to the. I mean, that doesn't in fact give you an unbiased sample either.
That's right. You have to somehow throw away energy, because obviously if I start up here and simulate just a particle with no initial random momentum and no way of getting rid of energy, the particle will easily go back up here again. And it'll spend very little time in the bottom case, so it'll be going very fast.
Yes, indeed.
And so it won't give you the distribution at all. But this business of every so often you throw away your momentum and sample it again, that'll give you the right distribution.
And do you need some, where does the randomness come in? There must be some randomness.
The randomness is in when you choose your new momentum.
Yes, but if you always choose it from distribution...
You have to choose it with a distribution with the right variance.
Yes, and what does that depend on?
Well, in my case, I got the code from Max Welling, and there was a variance of 1 in a Gaussian there, and that seemed to work just fine. So then I tried setting the variance to a 10th, and it didn't work at all. So then I concluded that actually there was an appropriate variance that was scaled by what your energy was like. And so given the sort of scale given you by the energy, then the variance is sort of, there's a natural temperature in this system of 1, right? If you want the Boltzmann distribution in this energy, at a temperature of 1, which is what we want, because that's how we define probabilities, then you've got this natural temperature of 1, and that determines the amount of noise you put in this momentum, and it's 1.
Okay, so I'm guessing that theoretically, any variance greater than 0 ought to work, but
no,
some of them work better than others in practice?
No, if you use very low variance, if you're adding very little noise, I think you can see that it'll spend all its time low down here, and that's equivalent to using a lower temperature. So the variance you add in the momentum is equivalent to the temperature.
Yes.
And so you can always do that if you like, and because if it can scale all the weights, if you use a small amount of noise, it'll just scale down all these heights, and you'll have a system just like you had before. So you might as well just set it at 1, because it can scale the energies, and it'll scale the energies to be appropriate for that temperature.
Thanks.
Okay, so here's what hybrid Monte Carlo looks like. You take your data, you do a forward pass, that's nice and efficient. You then do a backward pass through this network. So it's exactly the back propagation algorithm. And if there's a lambda on this, you go backwards through the lambda. And you come backward computing, as you go backwards, the derivatives of the total energy with respect to the values of the components of the data vector. So you get, if this is x and this is xi, you get the total by the xi here. So you come all the way back to the data, and those derivatives that you computed are now the slopes in the different directions of this surface, right? They're the gradient of that surface. So the nice thing is that if you have a multi-layer net like this, you can use the chain rule to get the derivatives here, even though this is a complicated nonlinear function. You can efficiently get derivatives here, and so you can follow the gradient in this space with any sort of nonlinearity. Okay, so what we've got so far is an algorithm that's going to be horrendously inefficient, because in order for the learning algorithm to work right, we have to add some random momentum, follow the trajectory, add some more random momentum, and just keep doing that gazillions of times. And on a big complicated energy surface, it'll take like forever to reach equilibrium. So it's a very slow algorithm, but it's right. What can we do to make it faster? Okay. So this is just a summary of the obvious, what I call the obvious algorithm. You start a data vector. You use backpropagation to compute for each of the parameters in your network the derivative of the energy on that data vector with respect to the parameter. You run HMC for lots of steps with frequent renewal of momentum. When you finish running your HMC, then you've sort of got bored and think, well, even if I'm not at equilibrium by now, I don't care anymore. Which is, you run this again to get this derivative, and then your parameter update, if you want to do just steepest descent in the parameters, steepest ascent in the parameters, is just some learning rate times this difference here. Okay? And the problem is this, that you have to run forever. So, the main content of this talk is the idea that this extremely optimistic and surprising shortcut actually works pretty well. In the learning rule, we've got the positives, what I call the positive samples, which are derivatives on the data, and we've got the negative samples, which are derivatives on the distribution the model believes in. So you really like to get sort of fantasies from the model for those samples. Instead of getting distributions from what the model believes in, we make slight corruptions of the data. Okay, so we take the data and we tell the model, okay, corrupt this data in the direction you'd like to corrupt it in to make it a bit more plausible under the model. So you're allowing the model to exhibit its prejudices. You're not getting it to do it very much, you're just letting it to change the data very slightly. And now the real Markov chain that goes to equilibrium consists of doing that lots and lots of times until you've forgotten where you started. But that's sort of daft, because even when you've just done it once, if the model's making systematic changes to the data, you've already learned a lot about what learning ought to do. It ought to try and stamp those changes out. So maybe we can get away with just adding the random momentum once, following the dynamics for a little while, and then we get what I'll call a confabulation. It's a data vector kind of reconstructed by the model, or affected by the model, so the model's been allowed to exhibit its prejudices, distorted towards what it would rather believe, but only a little bit. Now you've got something good, which is, if you look at these two terms, this is a data vector, and the balancing term here is taken from the equilibrium distribution, which can be anywhere in the space. I mean, it's all over the place, this. So this C is nothing like this D, typically. And so you have huge variance in this difference. If, however, you use these slight confabulations, almost all that variance goes away. If I corrupt the data slightly, then the negative term I'm using will be almost the same as the positive term. And all that variance will have gone. Of course, I'll get bias in exchange. And maybe that bias is going to kill me. Initially, you think probably that bias will kill you. But maybe we can view it as actually optimizing a different objective function. And actually, the conclusion of the talk will be, yes, we can view it as optimizing a different objective function, but unfortunately, it's not exactly following the gradient of this different objective function. It's following it much more closely than it follows the gradient of the likelihood, but it's only approximately optimizing this different function. Now, one nice thing about only using these slight corruptions is this. Suppose I had a perfect model. if I start at the data, and I have lots of data, a perfect model and an infinite amount of data, the kind of thing a statistician would typically assume, I now do a slight corruption of the data vector. That is, I take my infinite amount of data, and I run my Markov chain for one step. What will happen? Well, nothing will happen, right? Data vector A may change into data vector B, but equally, data vector B will change into data vector A. Actually, if there's more of data vector A than data vector B, the rate at which one changes into the other will be inverse to whatever. Detailed balance. When I run through this Markov chain, the distribution will not change. And so this learning rule I gave you, which just runs a Markov chain for a little time, it at least won't corrupt things when we got the right answer. That's very good news. So terminally, it'll do the right thing. And I think you can see that almost terminally, when you're very close to having the right distribution, it'll do very nearly the right thing. So it's beginning to look a bit better than just a sort of random kludge. So, I guess I've already said the intuitive motivation. I haven't got time to run this Markov chain to equilibrium. And the only reason I wanted to run it to equilibrium was to get some statistics or some gradients at equilibrium. And as soon as I've got them, I'm going to change the parameters, and so that equilibrium is gone anyway. I don't really care about that equilibrium. I just want to somehow figure out how to improve the parameters. And I can do that after the first step, or the first few steps, because I've already seen how the model is messing up the data. Okay? Let me give you an analogy here. Let's suppose you're teaching a student, you're teaching a graduate student, and we have to make certain assumptions here, which is the professor is always perfectly correct. And so you tell the student something, and then you could say to the student, tell me a random fact from your view of the world. And if the student tells you enough random facts, eventually you'll get the distribution the student believes in. Maybe then you'll be able to fix it up. But it's much better to say, tell the student something and say, okay, now you tell it back to me. And if the student tells you back the same thing, preferably in different words, and that shows he's got a Markov chain that's mixing. I mean, he can give you back the same thing by just having a chain that doesn't mix, by just parroting back. That's no good. He needs a Markov chain that mixes. So if he can tell you back the same thing in different words, you say, okay, you've got a good model. But if he tells you back something a bit different, you know how to fix up what he's saying, because he's sort of made this common mistake of assuming borrower. And we do that all the time, and that's basically this idea. Now, of course, what's wrong with that is if you take this student and you tell him what you believe, and he tells you back something that's pretty much the same, so you think you've got a good student. Then one day you hear him talking to somebody else about something, and it turns out he's got these completely crazy beliefs in areas you never talked to him about. That's certainly possible. And that's the same with these models. They could have these very deep energy minima, or very broad energy minima, very far from any data, and you'd never know it. Okay, so that's the drawback of this. Now the question is, in practice, is that really going to happen? In practice, is that going to kill you? Because theoretically it could kill you, but does it actually? And I'm going to claim it doesn't really seem to actually kill you. And one way of thinking about all this is, if you try and run your Markov chain by starting at random places and running to equilibrium, your big worry is this: if there's big energy barriers in this space, will I really get the right, will I really find all the modes of the distribution? And even if I do find all the modes of the distribution, will I get the right relative amount of mass in each mode? Maybe there's this big barrier, and half the time I'll go this side, and half the time I'll go that side when I start, but I ought to have 99% of my mass here, and 1% there, and I'll never cross this barrier after I've started, so I'll get the wrong amounts. But if you think about it, the data itself tells you where all the modes are, at least all the ones you need to worry about, and it tells you how much mass you want to have in each mode. So the data itself is telling you all this stuff. And so when you do this business of taking the data and corrupting it slightly, at least your negative examples are distributed among the modes correctly, except you miss big modes the model might have, but it shouldn't. And they've got the right amount of mass within each mode. So it seems crazy to throw away all that information and go for the equilibrium distribution. Now this transparency, I don't know if you can see it. It wasn't a very good picture. Can you see faint grey dots there? Yeah. Okay, so this was the two-dimensional example, and these faint grey dots are data that was generated at random. And this was an ICA-like case where you can see there's a ridge here, and a ridge here, and a ridge here. And independent components analysis is very good at picking up three ridges like that. But we also put data around here, around here, around here, around here. And independent analysis has great problems with that. This is showing you a view from above of the trajectories that hybrid Monte Carlo would take. And this is actually the data on which we trained this little model. And you can see now, the viewpoint's changed slightly, but you can see that it's got these three ridges. And then it's got the fact that this ridge joins up with this other ridge by this thing here, and there's a groove there, and a groove there, and a groove and so on. So it's modeled that data pretty well. It's constructed this energy surface. And to do that, you have to have more than just one layer of hidden units. That takes 2 layers of hidden units to be able to construct an energy surface. And at least you can equal the number of hidden units. And so this was our first example of this multi-layer net using just one full step of hybrid Monte Carlo. That is, random momentum once, and then go for about 20 iterations to follow the dynamics. And it does learn this just fine. The arrows here are the wrong way around, sorry. The arrow should say down. That is, we take the data and we lower the energy there, and we take some confabulation and we raise the energy there. The arrows are exactly wrong.
I don't think I understand. You've said it a number of times, so I think I'm just completely not understanding the language. We're looking at moving through theta. Theta's are the parameters.
No, we're moving through data space. This here, this is with fixed
So
theta.
we're generating samples of data.
Sorry, there's an outer loop where we're updating the parameters. That's what I call learning. And then there's an inner loop, which is this hybrid Monte Carlo,
Right, okay, so
where we're moving through the data space.
Right. So for a fixed set of parameters, theta, we're drawing realizations of data, and the fixed point condition for the maximizer is that condition that involves the parameters equals an expectation with respect to distribution or something.
The fixed point condition would be that this, when you do these samples, they don't go anywhere
I
around.
don't you keep saying that it's constructing the energy correctly. You said that numerous times. You've constructed the energy. I mean, you've written down a formula that is the conditional probability of theta given data. That's the problem. You've said a number of times it's constructing the energy correctly.
It's got a number of parameters theta.
Yeah, so
and they define the energy function, right?
right. The posterior probability is P of theta given X to data. X. And you're in this predicament, or we're all in this predicament because, P of theta given X is some random field. And so when we write down the maximum conditions for the derivative with respect to theta, we get this coupled condition that involves, the fact that P is a random field, and we have to take an expectation, it's hard to do. But that's where the energy is. The energy is in the model that you define. P of theta given X equals something. E of a bunch of potentials about theta.
Right.
So I'm confused. I think it's just language. It must mean something else. You've said numerous times when you look at this, we've said, look at how it's constructed the energy.
If I were to show you a movie of this during learning, in the movie, this crinkly surface here would start off flat. And what you see at the beginning was, we took a data point, which is exactly here, that's where one of the data points is. We run some trajectory, which initially was just a kind of random thing. Having run that trajectory, we now, the arrow is exactly wrong.
Good.
We lower this point and we raise that point.
Okay,
so it begins to get
the
crinkly.
sense in which it constructed the energy correctly is, it started with a theta that would give you a flat energy surface for that data, but we want to end up with a theta for that energy surface on the data, now you're supposed to be highly peaked with...
For that energy surface, you have an energy surface such that the data lies in the bottoms of ravines.
Okay. Right.
So that if you were to pick data according to e to the minus this energy, you get stuff that looks like the observed data.
So so that's what you mean by constructing.
Yeah. You learn the features. Okay. Now here's the hard sell. I'm going to argue that actually I've introduced this as kind of a hack that you couldn't be bothered to go all the way to equilibrium. And anyway, if you take one step, it's telling you to do it anyway. So maybe that'll work, and you try that and it does work. And then you start wondering, why does it work? And the argument is going to be that we're actually optimizing a different function. So maximizing the likelihood of the data is equivalent to minimizing the KL divergence between the data distribution P and the distribution that the model with its time set of parameters believes in, which I'll call Q infinity to indicate it'll take a long time to get that distribution. So maximum likelihood is equivalent to minimizing this KL divergence. And in fact, the magnitude of that KL divergence is how much worse your log pod is than the best you could get if two distributions are the same.
The infinity means you run the chain forever.
Yes. If you run it forever, it's certainly an station distribution, if it's the right connection. Okay. I'm going to say that instead of just minimizing this, we're going to minimize this and maximize this. Now, I put maximize in red, because if you ever dealt with KL divergences, you'll know that maximizing them is awfully easy. You just put in a 0 somewhere, and here you've got an infinity, and they're very easy to maximize. So that looks awfully dangerous to want to maximize one in your objective function. But the good news is that what I mean by Q1 is the distribution you get to after running your Markov chain for a short time, if you start at P and run the Markov chain. And if it's a Markov chain that comes with the guarantee that it's always getting closer to equilibrium, in the distribution sense, then this KL divergence has to be smaller than that. So this can't blow up. This quantity will always be positive unless it's 0, because this has to be smaller than that because of the way we got Q1 from P. Okay. So now, if you look at the derivatives of this, it turns out that the things you need to know about equilibrium, the statistics you need to know about the equilibrium distribution, cancel out, and you get this difference between the statistics you get at time 0 and time 1. So hey presto, of course this was made up post hoc to try and justify what I was doing, but I then actually went and measured this, and it really is following the derivative, this derivative pretty well. Now there's one little bit of weaseling here, which is it's exactly following the derivative of this thing if, when you change the parameters theta, you don't change Q1. That doesn't change Q1. But of course, when you change the parameters, it does change Q1. So there's an extra term in all this. That is, when I change the parameters, it'll change Q infinity, the equilibrium distribution the model is in, and therefore it'll change this KL divergence. It'll also change this Q infinity, and therefore it'll change this KL divergence. But there'll be a third term, which is it'll change Q1, because the Markov chain got Q1 from P using the parameters, using the energy function. And if we ignore that term, then what we're doing is exactly following this, we're following this gradient, the contrastive divergence, in the expected sense. But the question empirically then is that effect that we're ignoring, how big is it, and is it going to hurt us? And it turns out it's small and it doesn't hurt us, in all the cases I've looked at. So you can make up little nets in which it really screws you. But as soon as you take big networks, it seems that it's small, and actually it goes in the helpful direction rather than the helpful direction. So basically, you follow the derivative of this pretty well. So we got a double approximation. We really wanted to maximize likelihood, minimize this KL divergence. Instead of doing that, I say it's much more convenient to follow the gradient of this difference here, but actually we can't even follow the gradient of that, but we can nearly do that. So instead of doing the right thing, which is incredibly hard, you can do something that sort of you could argue for, but isn't quite the right thing, and you can't quite do that, but you can almost do it. But that's right, but at least it's quick. So now let me say a bit about applying this to images. As I said before, if you take a patch of image, it typically satisfies very well constraints. Like, for example, if I take some smoothly changing image like this one, and I plonk a filter like this on it, then I multiply the middle bit by positive numbers and the flanks by negative numbers, and then cancel out and produce 0. And that won't be true, of course, if I have a vertical edge across here. But notice it will be true if I have a horizontal edge. So now what I'm going to do is I'm going to try and characterize images not in terms of features that they have, but in terms of constraints that they satisfy. In linear analysis, this is equivalent to doing minor components rather than major components. It's equivalent to looking at the very small eigenvalues you get down one end rather than the very big eigenvalues you get up at the principal components end. There's information at both ends, and this is going for the small ones, because those are the constraints the data satisfies, the directions in which it doesn't vary. So you're looking for directions in images where you're not allowed to move at all. Okay. Now, so we have this filter, we involve the image with the filter, and we say most images will give us approximately 0 when we do that. The question is, what's our loss function? We could have a quadratic loss function corresponding to a Gaussian probability distribution over what we think violation should be like. That's the wrong thing to use here. Because what happens with images is they nearly always satisfy this fairly accurately. But when they don't satisfy it, they really screw up, because that will happen when you get an edge through here. And so the distribution of violations you get isn't at all Gaussian. It's a very heavy-tailed distribution, much more like a Cauchy distribution, or the negative log of a t distribution. So take an infinite mixture of Gaussians with some continuous distribution of the variances, with zero mean. Take the negative log of that, and it looks like this. And what that's saying is, when you're satisfying it, you're really concerned to satisfy it better, and you want it to be really sharply satisfied. If you've already violated it, it doesn't cost much more to violate it a whole lot more. Okay. So we're going to use that kind of energy function on the outputs of these linear filters. And so UIT took 100,000 patches of natural images, 16 by 16 patches from Van Handen's database. So these are carefully selected real natural images. He had a 3 times over complete network. So there were 768 terms in the energy function, each of which has 256 parameters. And we're just going to optimize the hell out of that. He's going to produce confabulations from the data by adding random momentum once, and then doing 30 steps along the dynamics. And then he's going to update the weights. It's going to be mini batch. It's not online, but it's not full batch. He updates the weights every 100 examples. And he adds a little bit of weight decay. A little prior that says that the filter should be smooth. Yes. And that's what he gets. So it produces a nice set of filters. Remember, the images look nothing like this. So he gets low frequency filters. That's a sort of DC component. He gets medium frequency ones. He gets lots of high frequency ones. And he gets a few of these checkerboard things. You can get rid of those by using various clever tricks of filtering the image. Basically, these come because the pixelation creates power in funny places. If you put a circular window on the Fourier spectrum and get rid of that power that comes along in that, you go away. Or you could do PCA and reduce the dimensionality of the data set and so on. So it gets a nice set of filters that look quite like what you get in the brain. There's other methods of getting these apples, like ICA. But they don't form a topographic map. Now, I have a sort of side interest in how the brain works. And it would be nice if this method actually formed topographic maps. So what you find in the brain of something like a cat, or a monkey, is you find filters like this of different frequencies and orientations. But you find them so that neighboring filters will have similar orientations, like those two do, but like these two don't. And like neighboring filters will have similar spatial frequencies. They'll also be in similar relative positions, we believe, although it's much harder for neuroscientists to see that. At a gross scale, they can say this topography, but at a fine scale, neuroscientists can't tell the exact position of these filters, for example, because it's all done with states.
What's the order here? It's
Random. Oh, sorry, UI ordered them by frequency retrospectively. So these are ordered by, UI ordered these by frequency. So he took a subset of them, but then ordered them by frequency. But now
there's no natural order in that. There's no natural order.
There's no natural order here because each of these.
So I understand the calculation of that.
Okay, that's going to come next. There's no map here. So if you want to get a map, oh, one other thing I should show is that if you take the set of 768 filters you got, you can look at how well they cover image space. And you do that by you fit a Gabor function to each filter, and then the Gabor function, once you fitted it, tells you an orientation, a position, and a scale. And you can now make a bar of that orientation, position, and scale so you can see it easier. And you'll notice it covers the space very nicely. Obviously at low frequencies you can only have a few. And you have to do things like, if at the lowest frequencies you've got some orientation gaps, you'd like to fill those in at the next highest frequency. You'd like to cover this 4D space of orientation, and scale, and position. And it's very hard to do that by hand. I mean, position you can cover by hand because you have a regular timing. But with a limited number of filters like this, it's very hard to cover this full space, and this does a very nice job, much better I think than you could do by hand. So now we wanted to run a topographic map, and we borrowed a trick that's been used by some ICA people, particularly a guy called Havainen in Finland. They use it in causal type models, and we can use the same trick in our models. So we have the image. What we were learning before was a set of linear filters that give energies according to this heavy-tailed negative log of T distribution. But now what we do is we have our linear filters globally connected to the image, but then we have a second layer of units. Neuroscientists call these complex cells, and these units receive local connectivity. So this green unit here just looks at all the ones in this patch. Okay? Notice each of these looks at the whole image. But by using an array of these guys, and by making neighboring ones here connect to nearby patches, we induce a topography over these guys. In other words, you can say that this guy and this guy are neighbors, and the reason they're neighbors is both of them connect to this green guy. If it was this guy and this guy over here, there'd be nothing up there they both connected to.
So that's a projected field. I mean, that is a projected field of the neurons.
If these have projections back, because it will be a projective field, yes. You can think of it as the receptive field of this is local. So basically, neurons that occur within the same little local receptive field you can think of as near in some sense. So we've now defined what near is, and by making these fields local all over here, we make sure that neurons that are actually near in this diagram are actually near in the connectivity sense of having lots of things they both project to. Okay, so we've got a topography here.
A little lost, I'll try your student game.
Okay.
So each of these filters is such that if you run it over all the sample of images, and you look at the histogram, so to speak, of responses, you get e to the minus that function. That's the distribution of the response.
If it could do what it wanted to do, that's what it would like to do, yes.
So these are all filters that come close to that?
Yes.
But how did you choose that particular set of filters? That wasn't clear to me.
Well, we've learned the weights, right? We've put this prior on what the violations ought to look like. Well, we said when they contribute energy by violating the constraint, this is how they contribute energy. Now, go off and learn weights so that on real data you have low energy, but on corruptions of real data you have high energy. Of course, initially, but the trick is the corruptions are made to try and lower the energy. So initially they'll take real data and it'll find some direction to go in that according to its current model makes it lower energy. And so you'll say to your parameters, don't go in that direction. Change the parameters so you don't like that direction. So you get big violations there. Just keep doing that. And I mean, initially you thought, well, why does it make all the energies be zero? Well, because then data would have no more probability than all these corruptions of data. What it wants to do is construct a minimum like this where the data's here and the corruptions are all higher. Okay, so now if you think about this curve, I don't know if you can see the green curve.
I have another question. You said that you take filters which are local. What is the notion of locality here now?
Okay, these connections are global. That is, each of these neurons connects to the whole image.
So in your earlier diagram...
But here, each of these guys just connects to a little local patch of these guys.
So that's my question is, in what sense are they local?
They're local in the brain, not in the image. But in the brain, imagine a bunch of neurons here, laid out in a 2D map, laid out in a 2D.
Okay, so in your hidden nodes, you're going to have some kind of notion of data.
Yes. So we're going to have, in the brain, it's actually physical neighborhood.
Yeah. Okay,
but of course,
I understand.
But in my computer model, if these are globally connected, it doesn't matter where I put them in the display, right? There has to be some functional definition of what being close to one another means. And the functional definition is, two guys are close if they connect to the same guy above.
Okay, so these are your two layers. Right?
Yes, there's two hidden layers here.
And some things in the upper layer.
And so independently of how I display these now, I can display this one over here. But as long as it's connected to this guy and this one is too, then they're close. Okay, so now something interesting happens. I'm going to contribute energies in the following way. These filters don't contribute energy at all. They can do what they like. It doesn't affect the energy. I'm going to square their outputs and then send their outputs to these guys. And it's these guys who contribute energy. They add up the weighted square outputs of the filters, and they contribute energy according to this heavy-tailed distribution. And so now, let's think about what happens if an image comes in and causes this filter to get really excited. that filter will send the squared excitation up to here. This guy will be way above 0, and I'll pay this cost. That's my log prog cost, the energy, for this guy, this filter having his expectation violated, having his constraint violated. If I also make this guy be way above 0, since he contributes to the same one, he'll add a little bit of additional cost, but because it's heavy-tailed, having two filters that are next to one another violated doesn't cost nearly as much as having two filters far apart violated. And so what this will do is it'll get correlations in variance. These aren't correlations at all, right? These are fourth-order things. These filters can be completely uncorrelated. When this is big and positive, this is big and negative sometimes, and big and positive other times. But if their variants are correlated, they both tend to be violated a lot at the same time. And then it's better to have them connected to the same high-level unit than to different ones. And you do that by having them next to each other. And so, other things being equal, what you'd like is filters that are violated at the same time in a natural image should be near one another. And filters, because of limitations of geometry, filters that aren't violated at the same time move far apart. And so here's what happens. So this is work by Simon Alcindero, and you see it's developing, it's not a very good display, okay, but you see there's a low frequency patch here. Because of the frequency distribution in images, if there's a big, powerful, low frequency thing, these low frequency things all get excited at the same time. So they tend to be near one another. And you'll see there's continuity of orientation here, and continuity of position. So for example, if you look at this filter, and say this filter, they're a similar orientation and similar position. And you can see a sort of, you can see the constraint. It's not very good, but it's okay. And we're beginning to get topography.
And then on the right side, it's just a circular boundary condition.
It's a torus case. So this is very good. This is the edge of this low frequency patch. So that trick works. It gets us topography. We can actually get topography better. So this is the sort of final bit of the talk. By using there's a faster mixing chain that I'm not going to have time to talk about, that Max Wanning constructed, where essentially you're sampling the variance for these filters, and it's more like alternating Gibbs sampling. There is a tech report, if you look up, if you do Google Hinton, and then look, the tech book, I'm about to put the tech report on my website, that describes all the details of this. You can get faster mixing with less computation. And then we can get nice topographic maps like that. This is a better topographic map. And in this we've learned, you're not seeing all of it. You're not seeing all of it here. It's about 45 by 45, it's about this size. There's about 1 million parameters that we've learned. And it'll learn about 1 million parameters in an afternoon. And you'll notice here you've got several low frequency patches. Again, this turns out with that. You've got much better continuity of orientation. You've got very good continuity of relative location. So all these filters are interested in the top right-hand corner in the image and so on. And we're beginning to get maps that look much more like what goes on in the brain. One advantage of vision over natural language is, you'd love when you do Max-N methods to be able to stick an electrode into a cat or a monkey or a chimpanzee and see if it has one of these Max-N features you believe in. You can't do that in natural language, but you can do it in vision, and you do find things like this. So, one other thing I wanted to say was I've introduced these two classes of models. There's these stochastic causal generative models. There's these deterministic energy-based models. The problem with these is the posterior distribution is intractable. The problem with these is you've got a nasty partition function. If you make a model with as many hidden units as there are components in a data vector, so where the matrix of connectivity between the data vector and the hidden units is square, then this posterior distribution collapses to a point. This is my experimentation with animation. And you get ICA. And what's more, the partition function becomes a determinant, and so the partition function becomes tractable. So ICA is actually in both of these classes. It's the version of these where it's not a Gaussian posterior, but its tractable physics acts to a point. And it's the version of these where the partition function suddenly acts to a determinant because it's a linear relationship between the of the features to the data. And so that's my summary of what I told you about. These have this problem. You could use simple models like mixtures of Gaussians or HMMs, or you could use complicated models and use Monte Carlo, or you could use variational approximations, and they're optimizing a different function. This I haven't talked much about, but actually, if you use a version of these stochastic links that False-Bernardsky introduced, you can then use alternating Gibbs sampling for just as you want hidden there, and then you can use contrasted divergence determinant. Or you can use these deterministic models, and notice being deterministic isn't an option. If you make these models deterministic, you can't generate a variety of data. Here you can be deterministic, and then you can overcome this by using contrasted divergence. Or you can say I'm going to pick the features in some other way and not try and co-adapt all their parameters, and then I can use these Maxent methods and iterative scaling. So those seem to be the two choices here. Now, I'm making no claims about this working better than what the language people do, especially for language. But I think it'd be worth experimenting with it to see how it compares. And it does have the nice feature that you can learn the features. Okay.
I missed step in the motivation for the last system that you talked about for having the energy contributed solely by the uppermost elements. When you conceive of those elements as doing computationally when you put this to work?
Okay, I mean, culture of neuroscientists, they're all very happy because those are just like complex cells, and what they're doing is they're pooling together the rectified outputs of filters. You're squaring the outputs of filters. So they will, over a small region of the image, they'll say, this kind of filter fits, but it might fit anywhere in that small region. So they're getting you a little bit of translation invariance, and they're getting you phase invariance. They're saying there's some oriented edge at a particular spatial frequency, but I'm not telling you the phase or the exact location. And if you do that in many, many layers, you keep rectifying and then pooling, and rectifying and pooling. I think if we apply this recursively, we can build a visual system. Certainly some neuroscientists or psychophysicists like Hugh Wilson believe that. But they don't know how to learn this stuff.
You're probably aware of this, but concerning this function, like x over 1 plus x, in the IEEE
1 plus x squared.
well, no, if you want it to be concave, so you want like x over 1 plus x. If you put x squared over 1 plus x squared over 1 plus x squared, it'll look like that.
Yeah.
Yours was
We need to be able to get out.
concave if you were.
Yeah, but, sorry, what I'm worried about is it has to be a proper
Yeah,
distribution.
but finite asymptotic behavior. So either x over 1 plus x or x squared over 1 plus x squared will both give you that finite asymptotic behavior. There's a series of papers in the IEEE transactions image processing literature in the middle 90s, I don't know, 92 to 98 or something, about a dozen papers that play with this function, applying it to filter responses, edges, for example, for various motivations that are analogous, not exactly the same, but analogous to the motivation.
I mean, we got this out of the ICA people, who presumably were helped to get from there. But as soon as you say that the violations of these things are going to be rare but big.
Sure.
Geoffrey, you finished your talk by saying, but it could learn features. That was your last feature. So I wanted to make sure. So in the Gibbs distribution, the parameters theta multiply things that we call potentials. Potentials are like the feature. Or the filter, in your case, you're the filters, you learn these filters. Is that what features are?
You're used to Maxent language models, I guess, where you have a little lambda in front of an energy contributed by a feature, and you just learn those lambdas. But the feature itself doesn't have parameters.
No, I understand. So the potentials that we shift around, if we want to shift it around the field, those potentials are what you mean by features.
Yes. Yeah.
Or, Mumford and Zurich, or Don calls those the filters, and we're showing those filters.
Yeah.
Okay, so those are.
Well, typically you have a filter which is linear and then some non-linear transformation.
Yeah,
Exactly. That's
those
the energy.
those are the things that we want, it's hard. It's like equivalent to the model.
Yeah. And that's what we want to work.
Any other questions? Let's